Okay, so welcome back. So the final talk in the series of lectures on Arakelov theory, equidistribution, and algebraic dynamics by Professor Butgos.
Okay, thank you very much. So I want to give some examples now of this dynamical system point of view. So the first, so this will be section, I think, of 3 examples. And then the first example will be just consider P1 over Q. And then the map F will be the map from P1 to P1 that sends the point xy to the point x to the n, y to the n. Then my line bundle will be just O of 1, and there is an isomorphism between F upper star of L is isomorphic to n times O of 1. Now we need to compute the invariant metric, and then we need to compute the curvature of the metric. But remember that there is a metric that has already appeared, which was the metric that says that the norm of the section X is given by the absolute value of X divided by the max between the absolute value of X and the absolute value of Y. And now if I look at what is the norm of the section X at the point x0n, y0n, then using the formula, this will be just the absolute value of x0 to the power n divided by the max of x0 to the power n and y0 to the power n. And if you see, this is exactly the norm of x at the point x0, y0 to the power n, which means that we already have the invariant metric. So this is automatically the canonical metric. Invariant. And you can see in this case that this metric is continuous, but it is not a smooth metric, because you can see that when the size of x and y is the same, we have a continuity, but it is not completely not smooth. So we want to compute C1 of O of 1 with respect to this norm. And this has to be like DDC of log of the norm of a section minus DDC of log of the norm of a section. And we can compute this DDC if we know how to take the derivative of currents. So this is a continuous function, in particular is bounded, so it will give us a distribution, and we can take derivatives of distribution. Or if we believe that things work well, we can heuristically see what happens here. Because for instance, if I look at the open set where the absolute value of x is bigger than the absolute value of y, then what is the value of the section? So the norm of the section x is just constant equal to 1. So we know that in this open set, this whatever good definition of derivatives I get, the derivative of something constant will be 0. So on this u0, we get 0. If I look at u1, this will be the norm of x strictly smaller than the norm of y. Then I get that the norm of x is just given by log, by the norm of x over y, or if you want x over y multiplied by x bar over y bar, and square. And now this function is harmonic, and the DDC of log of this function will again be 0. So we get, so u1 will be again 0. So this object has to be supported on the unit circle, exactly on the points where the function is singular. On the other hand, we also see that this function is symmetric with respect to rotations, only depends on the norm. And we also know that the total integral of this function has to be 1, because the degree of this line bundle is 1. Hence, we get that this guy has to be exactly the hard measure on the unit circle. There is no other possibility. And now we see that this example explains perfectly the experiment I made the other day. Because now if I look at a polynomial P such that, so P is equal to A sub D set to the D plus A 0. And this is not necessary, but just to apply the theorem, let's assume that it is primitive, irreducible, and that the coefficients are bounded. Then recall that the height of the root of this polynomial was given by 1 over d, then the integral along the unit circle of the norm of P of e to I theta. Differential of theta, and I think we have to put the log. Which in some sense means that if we make the, so if the coefficients are bounded, and in my experiment they were always between some -5 and 5, and the degree grows, this part here can grow at most like the logarithm of d, but I am dividing by d, so this means that this is going to 0. So then the bigger the polynomial I get, the smaller the height of the solutions, hence the solution will converge to the unit circle, which is exactly the curvature of the line matrix. Okay, so the equidistribution theorem that I presented explains why this root of polynomial converges to the unit circle. Of course, this is a very particular case because the same result will be obtained if instead of taking integral polynomials, I get real ones, and there is another equidistribution by Burgos-Durand that explains also the result. But in any case, this is a first example of how this equidistribution result works. Okay, second example, which is the one that we will be interested, is if I take a principally polarized abelian variety, and let's take as the line bundle the theta divisor, which is symmetric. And in particular, this implies that if I take n upper star of L, this is isomorphic to by some phi to n squared of L. Then I can apply the same methods as before and obtain an invariant metrized line bundle L bar, which is the one that whose metric is invariant under this action, and I obtain an associated height L bar, and this height is just the usual Néron-type height. And this is not surprising because how is defined the Néron-type height? The Néron-type height is defined by a limit argument, and in some sense the history is the opposite. So we have the Néron-type height, and what we are doing is to copy the definition to the Néron-type height to an arbitrary dynamical system. And we can also compute the C1 of L bar, and C1 of L bar will be just the invariant 1-1 Taylor form. So then, as a corollary, if I have A an abelian variety, let's say defined over Q or defined over a number field, and I have Xn, a sequence of points in A Q bar that is generic and is small. In this case, generic will be that no subsequence is concentrated in a subvariety, and small that the height converges to 0. Then the limit of delta of O of xn or g of xn, the Galois orbit of xn, this will be exactly this, let's call it omega. This will be exactly this form omega. So all small points will converge to the invariant. What? The meaning of generic means that no, so that all subsequents of the sequence have to be Zariski dense. That there is no subsequence that is concentrated in a subvariety. Okay. In fact, it's a good question because a lemma that I will need later, I can then explain now. So if I have X a subvariety which is defined over a number field, and I have a sequence Xn, a sequence of points in X bar that is Zariski dense, then we can always extract a subsequence that is generic. Okay. And this is clear because the set of subvarieties is countable, and then you can make a diagonal argument. You start with the points that are not in a subvariety, the points that are not in two subvarieties, the points that are not in three subvarieties, and then take a diagonal subsequence, and you will get a subsequence that is generic. Okay, so in some sense, generic or Zariski dense, you can go from Zariski dense to generic easily. Okay. Now we want to apply this to solve some Diophantine problems. So let's recall some known results. So the prototypical Diophantine problem is Mordel's conjecture, the theorem by Faltings, that tells us that if I have C, a curve defined over, let's say, Q bar, and the genus of the curve C is bigger or equal than 2, and if I have a number field, then the number of points in the curve in this field, this is finite. So this is a prototypical finiteness theorem. Here I am fixing the field of definition. And for instance, one would like to know not only that it is finite, but one would like to have a bound of this, of the number of points. This will be some kind of uniform model where you can bound the height. Other kind of questions will be the Manning-Mumford conjecture. Here I allow the field to be arbitrary, to be in K bar, but then I impose a different kind of condition. So the Manning-Mumford conjecture that was first proved by Renaud, and then there are many other proofs, says the following. Assume that I have C, a curve, again defined over Q bar, and the genus of C is bigger or equal than 2. Then I can look at the Torelli map, not the Torelli map, the Abel-Jacobi map that goes from C to the Jacobian of C with respect to some particular point. And then I can look now in G of C, I can look at points of defined over an arbitrary field, but torsion. So I can look at a CQ bar intersected with the torsion of the Jacobian of C. The torsion points of the Jacobian of C are again algebraic. Then the Mahan for conjecture tells me that this intersection is also finite. Okay. So the points, the algebraic points of the curve C that are torsion in the Jacobian is just a finite set. Now there is a generalization to higher dimensions. So this is for curves, but in some sense, one can do it for arbitrary subvarieties and can be written as follows. So this will be Mahan for in higher dimension. That will be the following. If I have an abelian variety defined over Q bar, and I have X, a closed subvariety what? Yes? I don't know. So any curve of genus bigger or equal than 2, yes, and you put in the Jacobian, the number of points of torsion point is finite. Yes. Yeah, but here is over Q bar, yeah. No, the point is that the torsion points are always defined over Q bar. So then a posteriori, they are defined over Q bar. Even if you start saying points of G, C. Lower or upper bound, you mean? No. No. I don't know, but possibly. The point is that you can change depending on the point you are having here, so it will change. I mean, the point is that this map will change. Yeah. Exactly, but then if you change the points, then it will possibly it will be empty. Yes. 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 I will later say something. Okay. No. If you look at over Q bar, the total number of torsion points is infinite. Because if they are defined over Q bar. So no, so the point is that this set is infinite because it's all the torsion points and this is defined over Q bar, so you can get higher and higher degrees. But when you intersect with the curve, you will get only finite number of points. But if you change the other embedding, then you will get another. But what do you mean? Yeah. So for instance, if you take complex points, then you can take all torsion points, and then for each embedding, you will find this torsion point, so you can get all torsion points using different embeddings. So this is for this embedding, not for this embedding. Okay. So in higher dimension, I have an abelian variety defined over Q. I have a closed subvariety of A, and then one can see that the X intersected with the torsion points of A is equal to the union for all I. So it's a union or sorry, this is equal to the union of some xi intersected with tor of A, where I is finite and the xi are special. in the sense that they are translated of a sub-abelian variety by a torsion point, which means that if you have a lot of torsion points on X, there should be a good reason. This should mean that there is a subvariety, an abelian subvariety contained. And in this way, for instance, this is related with the talks by Bruno Klinker, because there is a proof of this using these ominimality results. And this proof will not depend on being on QR in principle. But I want to give an arithmetic proof. Now, recall that since the Néron-Tate height is this height about dynamical systems, we already know that X inside A is torsion if and only if the height of X is equal to 0. So in some sense, we are looking at points of height 0. What? So special means that it is the translate of an abelian variety, of an abelian subvariety, by a torsion point. So this will mean to be special in this case. Okay. Now, recall that torsion means having height 0, and so this theorem can be, or this theorem here, can be stated saying that the points in Q bar that have height 0 have to be a finite number. But then Bogomolov conjecture at least for curves is a generalization of this result that says the following. So if I have C defined over Q bar and I have the embedding EQ from C to the Jacobian of C, then there exists an epsilon bigger than 0 such that for the set of points in X in C Q bar such that the height of X is smaller than epsilon is finite. So that not only the points with height exactly equal to 0 in Q in C is finite, but that I have really a gap. So if I look at all the points with height smaller than certain epsilon, there is just a finite number. So this is a big generalization of the Mahan-Manford conjecture. And this is the version for curves. What will be the higher dimensional version? So the higher dimensional version is that so I take A an abelian variety, define it again respect to Q bar, and X inside A is a closed, let's say, irreducible variety. And I will assume that X is non-special in the sense I have written before, that it is not the translated of an abelian subvariety by a torsion point. Then there exists an epsilon bigger than 0 such that the set of points X inside X of Q bar with height of X smaller than epsilon, this set is not Zariski dense. So this will be the analog, the higher dimensional analog. Observe that in particular, if X is any curve that is not special, this means that it is not an elliptic curve. So it has genus bigger than or equal than 2. Then there exists an epsilon such that this set is not Zariski dense. Not being Zariski dense in a curve exactly means being finite. So, and this is the result I want to give you a proof based on equidistribution results. So the first time one looks at these kind of results, says, oh, that should be easy. I mean, if I have a lot of small points, because I can find points of arbitrarily small height close to my variety X, then I can take a sequence of points. And this sequence of points, since they are in my variety X, will concentrate in my variety X. But since I have an equidistribution theorem, I know that they have to equidistribute to the uniform measure on the abelian variety, so it cannot be the case. But then you read again the statement, and the statement tells you that in order to have equidistribution, you need that your points, your sequence is generic, which means that you have to exclude the possibility that they are contained in a subvariety. So you need to work a little bit more. So you need a nice idea to use the equidistribution to show. What? Well, that's true because, so you know that this, so in this case, you know that this set is finite. So there will be a bunch of finite, a bunch of torsion points and a bunch of finite elements. Now you look what is the minimal height of these non-torsion elements, and then you go to the. And? Yes. Okay. What? Where? No, here there is no finiteness. The problem is that here I have a subvariety. Okay, if it is not special, but it can contain special subvarieties of a smaller dimension. And the only thing I can say is that there is an epsilon such that the elements with a height smaller than epsilon is not Zariski dense. But still it can be infinite or. I am not sure. Oh, well, the point is that it is not Zariski dense. Now you can say, okay, let's look at the closure of these guys. Then the closure of these guys will have to be an special subvariety, because in this closure will have an element that is Zariski dense. So your original variety contains an special subvariety. So in some sense you can express this way. Well, the point is that once you have a special subvariety, then you have a lot of torsion points. Of course, because it is translated from an abelian variety by a torsion point. So of course. Eh? No, because inside this abelian subvariety, you will have points of arbitrary small height, as long as they are in a special subvariety. So in a special subvariety, you have the torsion points have height 0, but you will have a lot of points of small height inside this variety. You can only do that in the one-dimensional case where you only get a finite number of points. And then at the end, you can say that they have to be. Okay. So let's try to make the proof. And the proof will be by contradiction. So let's assume that I have, assume that I is an abelian variety, defined over Q bar, and I have some Y inside A, and that contains a sequence xn such that the height of xn converges to 0, so that I can make it arbitrarily small, and that is Zariski dense in Y. Okay, and then I want to prove that it is necessarily a special subvariety. Now, the first observation is that I can look at the stabilizer. Let's write G of Y, which will be the elements in A such that Y plus A is contained in A. So the stabilizer of the subvariety A. This will be an subgroup of A, and I can take the quotient group. So I can consider A mod this G of Y, and then the image of Y. Okay, So then I can assume that y has 0 stabilizer. And then now the problem will be not to prove that it is special, because since I have killed the stabilizer, what I now have to prove is that then it is a point. What I have to prove is that if I have a subvariety that contains a Zariski dense small sequence, and the stabilizer of this variety is 0, then it has to be a point, just one point. Okay. Now we will use a small lemma. Okay. No, I am not saying that y is translated. So I am saying I have a subvariety y, and then I can consider the stabilizer, and then I can take the quotient by the stabilizer. Now the new subvariety will have no stabilizer. So now the theorem that I have to prove is that if I have a subvariety that contains a dense sequence of small points and has 0 stabilizer, then it must be a point. A point, a dimension 0. Yeah, because I have killed the possibility of being a translator of abelian variety because I have killed the stabilizer. Okay. So now I will need a small lemma. Okay. Yeah, so if this one is a point, then this one will be just the stabilizer, the original stabilizer times the point, so it will become the translator of abelian variety, exactly. Okay. So now I want to prove the following lemma. Is that if y, so if the stabilizer of y is just the identity element, then there exists an m bigger than 1, such that the map phi that goes from y to the power m to x to the abelian variety a to the power m minus 1, that sends a point of the form 1 y1 up to ym to y1 minus y2 up to y, or maybe y2 minus y1 up to ym minus ym minus 1. So this map that goes from the nth product of y to a minus 1, that is the difference of these elements, is a generic embedding. Okay. Observe that in principle, for low values of m, maybe this is not possible. No, imagine that y is an hypersurface, then y to the m will have bigger dimension than a to the m minus 1. But the bigger the m, the dimension of the side grows quicker than the dimension of the side. So it's plausible that this will be at least generically an embedding. The proof is not difficult. So we need to prove, since this map is proper, we only need to prove that there exists one point that has that the fiber has one element. So we only need to prove that there is a point with the fiber e minus 1 of x is just 1 point. So now for this, I do the following. If I choose x1 up to xm, then I define g of x1 up to xm. So this belongs to y to the m. So all the elements are in y to the m. Then I define this thing as the elements A on the abelian variety, such that x1 plus A, x2 plus A, etc., xm plus A, all of them are still in Y. Okay, so I have a finite number of points, and then that belong to Y, and I look at the elements of the abelian variety that when I move the point, they are still in A. Okay, now we can see now two things. That if I take a finite intersection of points of sets of this type. It will be of the same type. Because, so this is a set that is given by certain conditions. If you want to make the intersection, you just have to put together the conditions. So this just means that you have to put more points, and the intersection will be of the same. But on the other hand, I had this hypothesis that says that the stabilizer of the whole set is just the identity, which means that adding points, I can make the stabilizer smaller and smaller. And at the end, since g of y is E, there exists x1 up to xm such that, or xy up to xm0 such that g of x1 up to xm0 is equal to E. Okay? But now the point is that is now easy to see that the fiber so that the phi minus 1 of a point x1 up to xm is exactly g of x1 up to xm times the point x1 up to xm. So once I have a set that has a stabilizer equal to the entity, I have a point whose fiber is just 1 point. Okay. Okay, so this is a small lemma. And now I started with my sequence. So I have now my sequence xn is a sequence of points in y u bar that is Taritsky dense, and that is small. So the limit when n goes to infinity of the height of xn is 0. Now I choose an bijection alpha from the set of natural numbers to the product of, yes? Yes? Yes. Yes, exactly. Oh, sorry. So it's phi minus 1 of phi. Yes. It's just that point, exactly. Exactly. So now I take alpha, a bijection between n and nm. So then this will be written, n goes to alpha of n. That can be written as alpha 1 of n up to alpha m of n. And then I claim that if I look at the sequence yn is equal to the point x alpha of n, alpha 1 of n up to x alpha m of n, the sequence is, so yn is a sequence in y to the m of q bar, and again is Taritsky dense and small. Okay. And alpha is a bijection, any bijection between n and nm. And then, so I can start with my small sequence, and then I can make a small sequence in a finite product, just using a bijection between n and n. And this sequence will still be Taritsky dense and small. And of course, since it is a Taritsky dense sequence, by the lemma I have written before, I can extract a generic subsequence. So there is a generic, so I can assume that the sequence ym is generic. Okay? But the same is true for the sequence phi of ym inside phi of y at 2 the m. Okay, so I have my sequence that is made of small points, and it is a Zariski dense small sequence and a generic, and then I look at the image of this sequence in phi of ym, and then I have the also a small sequence. And now the point is that I will apply the equidistribution result to these two sequences. So I will apply the equidistribution result to the sequence of points yn inside y, and I will apply the equidistribution result to the sequence of points phi of ym in phi of y, and try to see if I get a contradiction. Now, since in particular all these points live in the abelian variety and they are small in the abelian variety, one can prove that the line bundle with respect to which I am computing the height is the line bundle on the abelian variety. Then the curvature of this line bundle, when I see it on the subvariety, will be just the restriction of the curvature of the line bundle on the abelian variety to the subvariety. So this implies that the sequence, so the sequence delta of the orbits of yn, this converges to the measure omega 1 plus omega m to the m plus d, where omega I is just taking this form omega, the invariant form on the abelian variety, and then the if projection, the pullback of the if projection. But will be Zariski dense. No. But so what I say is that it is generic inside this guy, not in the abelian variety, inside this guy. Okay. So this guy is this restricted to y, not this on the abelian variety. It's this in y. So I am just looking. So I am applying the equidistribution. This is why the equidistribution was phrased in a general thing. So in a variety X with a line bundle with a metric, and I have a small point. So I am not applying in the abelian variety. I am applying this in y. And? No. And then now we look now at the and if I look now at delta of g of phi of ym, the Galois orbit in the image, now this will converge to omega 1 plus omega m minus 1, because remember that the image is contained in the m minus 1 fold product to the md. And having that this sequence of points converges to this measure, and this sequence of points converges to this measure, this automatically implies that this guy here, omega 1 plus omega m to the m times d, has to be equal to phi upper star of this omega 1 plus omega m minus 1. Everything, so this is restricted to y, this is restricted to phi of y to the power md. Okay, because we have, in some sense, the same sequence converges to these two measures. So these two measures have to agree. But now, the key point is that in all the smooth points of y to the m, this is a perfectly positive metric. It's a smooth, strictly positive metric. But this guy in the diagonal of y to the m vanishes. Hence, they cannot be equal. Okay. This is clear? Yeah. So the point is that this guy on y to the m is a smooth, strictly positive form, because it is just the restriction of a Kähler form. And then you take the maximal product, so you get a volume form, which is strictly positive and non-vanishing everywhere. This guy here, by contrast, the map phi on the diagonals get, because in the diagonals we are getting these differences, so this form here cannot be strictly positive on the diagonals. So these two guys cannot be the same. So this gives me a contradiction. Unless there are no diagonals. That is, unless m is equal to 0. So then this implies, so since they cannot be equal in the diagonals, not m has to be bigger, d has to be 0. So the only way there is no contradiction is when the dimension is 0. So then this implies that d has to be 0. But d is the dimension of y. Hence, y is a point. So we have had to use the distribution result, not on the abelian variety, as we were planning to do originally, but we have to do it in two varieties, y and phi of y, and show that then they cannot converge to the same measure. Questions? Okay. And at the end, so it has to be a point, but since it contains a sequence of points that converge to 0, it has to be a point of height 0, hence it has to be a torsion. Hence the original variety has to be translated of an abelian variety by a torsion point. So let me say now some words about recent developments, because this, what I have explained here is the original proof by Ullmo and Zhang. So this is the idea of Ullmo and Zhang, and this is from the 97, something like that. And there has been many nice developments. So I hope that these lectures will encourage you to study the recent literature in the topic. And let me just give a brief description of what has been the latest news in this area. So now they have been, okay, yes. So these are results by Dimitrov, Gao, and Habeger, by Kuhn, and by Yuan. So they started this Dimitrov, Gao, and Habeger. They were able to give a uniform Bogomolov that I will explain briefly, and it was improved by Kuhn, and then Yuan was able to improve even further and give a different proof of this fact. And this is the following theorem. So I will write the version by Yuan, which is the last one. Now let K be either Q or K of T, the function field of a curve. So the theorem is uniform in the number field case and in the function field case, where K is any field. So it works perfectly in positive characteristic or in zero characteristic. Now let G be a number which is bigger than 1, a positive integer. Then then there exists constants C1 and C2 bigger than 0 that only depend on G. And such that for any smooth projective curve. Projective curve. C over the algebraic closure of K of genus G. And for any line bundle L of peak of the curve C of degree 1 such that the pair C and the line bundle is isotrivial. So this is a condition that only affects the case of K of T. And this means that my curve and line bundle is not something which is defined over small k and then pull back to K of T. Because in this case, I will have a lot of small points because or a lot of points of height 0 because it will be just the points on K. So I need that it is non-isotrivial, that probably something happens. In the case of a number field, this is automatic. I don't need to ask it not to be isotrivial. Then, such that yeah, so the point is that in the function field case, I have imagine that I am looking at a curve over K of T. Now I have that K is included in K of T, which means that I have a map from a spec of K of T to a spec of K. Now it might happen that I have a curve over spec K and I have just the pullback here. Then the problem is that this kind of curves tend to be many algebraic points or many small points. So in order to get finiteness result, you have to exclude these kind of things. So you want something that is really moving, that is non-trivial with respect to this condition. And then what we get is the following. The number of points x inside the curve, so the number of algebraic points, such that the height of the point x minus alpha. So I use this, let's put alpha here. So I use this line bundle of degree 1 to define the map to the Jacobian. So for any point, I can consider the point x minus alpha as a point in the Jacobian, and I can look at the Néron-type height of this point of the Jacobian, and then I ask this height to be smaller or equal than the first constant, C1, times the maximum between the Falting's height of the curve C and 1 plus the height of the point 2G minus 2 times alpha minus the canonical bundle of C over K bar. Okay, so C1 times this is maximum, this thing here. So this set is smaller or equal than the second constant C2. Okay, so just one point is that we can say that we have just one constant C1 and a constant C2, such that the points with height is more than C1 is bounded by C2. But in some sense, these terms are improving the result because they are telling me that if my curve has very high Falting's height, I can make this constant bigger. And even if I look for points of higher height, it still will be bounded by C2. And the same happens with this term. So this term is positive, and again, it's improving the result. So you can, so if you want a result that only has two constants, you can write it with these constants, but these two terms is telling me that if you are looking for a very complicated curve, then you can even ask that the height of this point is very big. Okay, so, and you see that these two elements, these C1 and C2 are completely homogeneous. So they are the same everywhere. They only depend on the genus. Okay, So what is the consequences of this result, for instance? So a nice corollary of this is that it allows us to give it allows them to give a uniform Mordell-Lang result that will be as follows. So, and this one I will write it in terms of complex numbers. So there exists a constant C that depends only on the genus G, such that for every C, every curve defined over the complex numbers, and every point P inside this curve defined over the complex numbers, and every subgroup gamma inside the abelian variety, an abelian variety A, let's say the Jacobian of C, which is a finite generated abelian subgroup over the finitely generated subgroup gamma inside this Jacobian. The number of rank rho, the number of points inside EP of C intersected with this subgroup gamma, this number of points is smaller or equal than this constant C that depends on the genus to the power 1 plus rho. So that we get a uniform Mordell-Lang result in the sense that the number of points of the curve with any subgroup is bounded by a constant that depends only on the genus of the curve and the rank of the subgroup. So for instance, you can apply this to the algebraic points of your abelian variety, that you know that it is a finite subgroup of the abelian variety. And hence this will tell you that if you look at the algebraic points of the variety, of course, the algebraic point of your, so if your point P is algebraic, the algebraic points of your curve will give you algebraic points of your variety. So then you get a uniform bound in the number of algebraic points of your curve that depends only on the genus and of the Mordell-Weil rank of the Jacobian of the variety. And in some sense, this theorem is the root of this result is that if one looks at the original proof by Faltings and Boita and Bombieri of the Mordell conjecture, that you can get a bound so that the number of points is finite. In some sense, this proof what tells you is that if you look for points of bigger height, the points of bigger height is finite. Now, since you have Northcott property, since the points of bigger height is finite, only remains the points of small height, and then it has also to be finite. But you have no control on how many of them you have. But now, with this uniform Bogomolov result, you have that you can also bound the points of small height. So then you get that combining these two results, you can bound exactly the points of all the algebraic points. Okay, I will stop here.
Questions, comments, remarks?
No, I don't know. But they in this arithmetic tend to be terrible, but I am not sure in this case how it is. Sorry.
Any further questions, comments, remarks?
I am afraid that they are mostly that they exist, but I am not because since they have to be true for all G's, at the end they reduce to some existence. But don't take my words by granted because I have not looked at this in complete detail. In this case.
Any further questions? If not, let's thank Professor Burgos for his insightful lectures.